Thank you for joining this Anritsu webinar. I am Imoeko Jimba from Anritsu Corporation Sensing and Device Company. Today's presentation is entitled 120 Gbaud Wideband Linear Amplifier towards 800 Gigabit Ethernet 1.6 Terabit Ethernet Transmission Technology. Here are the contents of this webinar. To start, I'll introduce market trends, followed by Anritsu's device technologies and products. Next, I'll show the design method, points, and specifications for this wideband linear amplifier. Then, I'll introduce actual application examples, and finally summarize my talk. First, I'll introduce market trends. IP traffic is increasing at a high growth rate, driven by applications such as social media, internet protocol, video, and cloud services, with traffic volume reaching 300 exabytes per month in 2021 and increasing 3.2 times by 2022, growing at a rate of 26% per year. In this situation, higher transmission speeds are important for network expansion as projected traffic volumes increase. Currently, 400 Gigabit Ethernet is beginning to be widely used, but as this increasing trend shows, 1 tera class transmission capacity will soon be required. In particular, networks within hyperscale data centers operated by IT giants are accelerating their transmission speeds. To increase capacity, the IEEE 802.3 Ethernet Working Group is standardizing high-speed, high-capacity optical interfaces in various ways. For 100, 200, and 400 Gigabit Ethernet, to increase the transmission capacity per channel to 50 and 100 gigabit per second, multi-leveling from NRZ signals to PAM4 and multi-core and multi-wavelength signals with 4 or 8 lanes are being introduced. 53 Gbaud PAM4 has been used for the first time to transmit 100 gigabit per second over a single channel. Currently, the IEEE 802.3 DJ task force such as 200, 400, 800 gigabit per second, and 1.6 terabit per second Ethernet is considering further speed increases to 200 gigabit per second per lane, etc., making faster optical interfaces increasingly necessary. A transmission system using 100 gigabit per second times 8 lanes will be the lead choice to balance demand for high capacity with cost. The market will grow when 4-lane systems are deployed, and standardization has started for 800 gigabit Ethernet with 8 lanes each of 100 gigabit per second followed by 4 lanes each of 200 gigabit per second. For 1.6 terabit Ethernet, 200 gigabit per second times 8 lanes have been standardized, and 100 Gbaud PAM4 transmission is expected to become mainstream for 800 gigabit Ethernet and 1.6 terabit Ethernet. The optical measurement field is also expected to support this technology. With the increase in speed of 200 gigabit per second signals at 800 gigabit Ethernet and 1.6 terabit Ethernet, high-speed optical devices, such as optical modulators, as well as evaluation methods are required. The IMDD modulation method requires PAM4 signals of greater than or equal to 2 volts peak-to-peak and 112 Gbaud, while the coherent method uses PAM4 signals of greater than or equal to 2 volts peak-to-peak and 118 Gbaud. This will require a signal source with pre-emphasis peaking and a 120 Gbaud PAM4 linear amplifier. Next, I'll introduce Anritsu's device technologies. Our sensing and device company develops high-speed digital ICs and high-frequency amplifiers using the high-speed HBTs mentioned above with various functions for Anritsu measuring instruments. Our devices supply with high specifications that are difficult for other companies is the basis of our product competitiveness. In addition, we also release packaged module products for R&D. This slide shows some examples of recently developed devices used in our own measuring instruments as well as module products for R&D. Anritsu develops and manufactures measuring instruments for mobile, optical, and RF microwave communications, and have compound semiconductor fab at Atsugi headquarters, which manufacture high-speed ICs for the front end of our measuring instruments. Anritsu's indium gallium arsenide, indium phosphide HBTs feature as follows. 1. Top-class high speed achieved by self-aligning process. 2. High reliability with passivation ledge construction. 3. In addition to the previous FT over 200 GHz process, called Gen 1, supports even higher speed for FT over 300 GHz process, called Gen 2. The following basic technologies can achieve a Gen 2 process HBT that is faster than the existing Gen 1 process. Epitaxial structure design for achieving a high FT, reducing the emitter width, establishing a high reliability process technology, and high precision device modeling for circuit design. In particular, the emitter width is reduced from 1.0 to 0.5 micron. In addition, we plan to develop next-generation HBTs to support faster speeds. Anritsu has launched products manufactured on its own production line. Some examples are a 32 gigabit per second LN driver, 56 Gbaud differential linear amplifier, and 56 Gbaud wideband OE converter. These products were primarily manufactured using a Gen 1, 1.0 micron process, supporting bandwidths up to 60 GHz. This section explains the linear amplifier development. Increasing the speed and capacity of optical interfaces requires broadband linear amplifiers supporting PAM4 signals beyond 100 Gbaud. To meet this market trend, the AH15199A 120 Gbaud ultra-wideband linear amplifier was developed. This product was designed to be used as a driver for 800 gigabit Ethernet and 1.6 terabit Ethernet coherent Mach-Zehnder modulators and IMDD modulators, as a front end for semiconductor testers and optical measurements required for high-speed interface beyond 120 Gbaud, and for evaluation of optical devices and modules. Therefore, the development was started with the following target specifications: maximum operating baud rate of 120 Gbaud, output amplitude of 2 volts peak to peak, bandwidth of 100 GHz or higher, small signal gain of 16 dB typical, input-output interface with W1 connector, and dedicated power supply. Before developing the linear amplifier, we first selected the process. The blue and the red FT and FMAX lines represent the existing Gen 1 process and new Gen 2 process. Compared to the Gen 1, the Gen 2 has a higher FT and FMAX. High-frequency amplifiers generally require a maximum frequency FMAX of 2 or 3 times the operating frequency. Therefore, 0.5 micron process, Gen 2, with a higher FMAX is used for this amplifier. The ultra-wideband linear amplifier design uses the Gen 2 process. This figure shows the block diagram. A flat gain from low to high frequencies is essential to achieve a high baud rate pulse response. This product uses a distributed amplifier circuit to support speeds beyond 100 Gbaud. These are the small signal characteristics of the designed IC measured using the Anritsu vector star ME7838D. The red, blue, and black lines represent S11, S22, and S21, respectively. The small signal gain was 17 dB and the -3 dB bandwidth in the high frequency range was 113 GHz, resulting in characteristics such as high gain, high power, and flat gain. The small signal gain target of 16 dB and the high frequency bandwidth target of -3 dB at 100 GHz or higher were both achieved. The key to this IC is that it is designed for peaking at around 100 GHz, considering the module assembly loss. Next, I'll explain the module design. A target-achieving trial IC module was prototyped using the previous assembly method. Signal input-output from the IC is through transmission lines and connectors, with DC block capacitors mounted in the transmission lines. Quartz, which has a low dielectric constant and a proven track record, is used for the transmission line. W1 type connectors supporting over 100 GHz were used. These are the small signal characteristics of the module assembled using the previous method measured by the Anritsu vector star ME7838D. The previous assembly technology has unstable resonance characteristics beyond 60 GHz. The small signal gain target of 16 dB and the -3 dB bandwidth of 60 GHz were confirmed, but the 100 GHz target was difficult to achieve. Therefore, development of the assembly was necessary to achieve a wideband linear amplifier beyond 100 GHz. Precision simulation was used to achieve an assembly method for 100 GHz. The red and black lines represent simulation and measurement results, respectively. The simulation reproduced measured reflection and transmission characteristics up to 150 GHz, including resonance beyond 60 GHz. A new assembly supporting beyond 100 GHz was designed based on the simulation results. This 100 GHz band assembly design has three key points. First was to strengthen the quartz transmission line ground. We used grounded coplanar waveguide and simulated and optimized the via number and positions to strengthen ground. These are the quartz transmission line simulation results. The previous design suffered a large drop at 140 GHz, and the -3 dB bandwidth was 130 GHz. However, the drop disappeared with the new design and the -3 dB bandwidth was confirmed beyond 160 GHz, for an extension of more than 30 GHz. Second was to integrate the structure of the metal package and transmission line. Simulations determined the optimal ground connection method between the connector and quartz. Third was to use a design considering impedance mismatching. Optimizing the wire bonding between the IC and transmission line prevented the mismatch. The graphs show the simulation results. Although the previous design was unstable due to resonance above 60 GHz, the new design with integrated structure suppresses resonance and provides stable characteristics. Here are the simulation results for previous and new assembly design comparison. In the previous design, multiple resonances were observed beyond 60 GHz, resulting in unstable characteristics. Therefore, we strengthened ground of the quartz transmission line, integrated the structure of the metal package and transmission line, and designed by considering impedance mismatching. As a result, the new design suppressed resonance beyond 60 GHz and confirmed characteristics compatible with the 100 GHz band. These are the measurement results for the previous and new assembly design comparison. Experiments confirmed the improved design, suppressed resonance beyond 60 GHz seen in the conventional design. The -3 dB bandwidth was extended to 107 GHz, achieving an ultra-wideband linear amplifier module in the 100 GHz band. These graphs compare the simulation and measurement results for the new assembly design. The blue and black lines represent simulation and measurement results, respectively. Both the measured and simulated reflection and transmission characteristics up to 150 GHz were confirmed to be in close agreement, confirming the assembly design techniques for the 100 GHz band. 3 power supplies and voltage sequences are required to optimize the amplifier IC characteristics. We developed a dedicated power supply AH15199A-01 for easier amplifier use. The schematic shows the power supply voltage sequence. 3 power supplies are needed to drive the IC. The voltage rising edges control the power on timing and are designed to apply the 3 power supplies to the IC in the correct sequence. The falling edges are similarly designed to turn off each power supply in the optimal sequence. This dedicated power supply optimizes the amplifier's characteristics. From here on, I'll explain the amplifier's characteristics. Here are the ultra-wideband linear amplifier module AH15199A dimensions and configuration. The external dimensions are 20 mm width by 61 mm depth by 25 mm height, including the heat sink, with W1 connectors for the 100 GHz band and a bias port for the power supply. The dedicated power supply is 139 mm width by 74 mm depth by 22 mm height. It includes an AC adapter as a standard accessory and can be used with a single power source. The module is powered and driven by connecting the dedicated power supply using the dedicated DC cable. Pressing the single power button supplies 3 powers to the module in the correct sequence for ease of use and optimum module performance. Next, this explains the amplifier characteristics. First, the small signal characteristics were measured using Anritsu's 145 GHz band vector network analyzer ME7838D. Here are the evaluation results for the amplifier's small signal characteristics. The red and blue lines on the left graph represent S11 and S22, respectively, and the right graph shows the S21 results. The S11 and S22 parameters have excellent reflection characteristics of -12 dB or better at below 65 GHz. The amplifier has a small signal gain of 16 dB typical, a bandwidth from 200 kHz to 105 GHz, and a flat gain beyond 100 GHz. The next slides show the pulse response characteristics. The left figure is the measurement system schematic. Pulse response characteristics beyond 100 GBaud were measured using various fixtures such as clock divider and DAC. This compares the input and output waveforms at 112 GBaud observed using a sampling oscilloscope. The top right diagrams show NRZ signals and the bottom show PAM4 signals, with the input signal waveform on the left and the output from the AH15199A on the right. Both input and output waveforms show equal eye openings, indicating linear amplification. The rise time Tr and fall time Tf of the output signal are less than 5 picoseconds, showing excellent characteristics. A 2.0 volts peak-to-peak output amplitude is possible at 112 gigabaud. Here are the 120 gigabaud evaluation results. Like the previous slide, the top shows NRZ signals and the bottom shows PAM4 signals with the input waveform on the left and the output from the AH15199A on the right. This amplifier can operate at up to 120 gigabaud and has an output amplitude of 2.0 volts peak-to-peak. As the last characteristic, I'll explain linearity measured using the evaluation system shown on the left. The 1 dB compression point at 50 GHz frequency is 15 dBm, confirming the excellent amplifier linearity. This section explains application examples. Two AH15199A units can be combined as an equivalent differential amplifier. It is not fully differential and cannot eliminate common mode noise. However, combining two units can amplify differential output waveforms. This is a schematic of the measurement system. Like single operation, the pulse response characteristics over 100 gigabaud were measured using various fixtures, such as clock divider and DAC. These are the 120 gigabaud evaluation results for two AH15199A units combined as an equivalent differential amplifier. Like the previous slide, the top shows NRZ signals and the bottom shows PAM4 signals with the input waveform on the left and the output on the right. Using two amplifiers as an equivalent differential amplifier supports excellent data with a high output amplitude of 4.0 volts peak-to-peak at 120 gigabaud. Lastly, I'll summarize this talk. Anritsu has its own compound semiconductor fab manufacturing high-speed ICs. An ultra-wideband linear amplifier has been designed using our own process fab. The assembly technology supporting 100 GHz band has been established and the AH15199A ultra-wideband linear amplifier has been designed. As a result, a 15 dB flat gain beyond 100 GHz and 2.0 volts peak-to-peak output amplitude at 120 gigabaud have been achieved. Using two AH15199A units as an equivalent differential amplifier achieves a high output amplitude of 4.0 volts peak-to-peak at 120 gigabaud. Please contact us if you have any questions or need a quote. Thank you for your attention.